We are going to begin with Newton's second law. Now, if we recall, I'll do this in red, the first law said acceleration equals 0 when the net force acting on an object equals 0. And that told us that mass likes to continue doing what it's doing and forces change that. Well, in the second law, what we have is an explanation of how forces change the motion of an object. So the first way to write it is that the sum of forces equals the mass of an object times the acceleration of an object. I like to write it a different way. Acceleration is the sum of the forces over the mass. So this again tells me some more things about forces. 1, forces change the motion of an object. Or change the velocity. Change the velocity or accelerate the object. 2, more net force gives more acceleration. So if we look at this, what we see with the acceleration, or another way to talk about acceleration is to talk about it as change in motion. If the force goes up, then the acceleration has to go up. They are directly proportional. Force is directly proportional to the acceleration. The more force I have, the more acceleration I have. Or the more force I have, the more change in motion that we're going to see for an object. The third thing we see is that inertia, or mass, is gives less acceleration. Essentially, the more mass I have, the harder it is to accelerate. So here, if the mass goes up, then the acceleration is going to decrease with the same amount of force. The way we say that is mass, or inertia, is inversely proportional to acceleration. Okay, this is how the second law works. So we're going to look at all parts of it. Sum of the forces equals mass times acceleration. This is telling us what to do. Add up all of the forces. And that's going to be equal to the mass of my object times the acceleration of my object. So let's look at a quick example of that. Let's say we have a 5 kilogram mass. Let's say we have 4 forces acting on it. We have 15 newtons this way, 10 newtons this way, 50 newtons down, and 50 newtons up. Now, just to give us a hint of what may be coming up, this is a free body diagram. It's a force picture of all of the forces acting on an object. Okay? And it's just the forces acting on a single object, a single free body. That's why it's a free body diagram. So, the question here is, what is the acceleration of the mass? So what we have to do is look at our formula that talks about acceleration. The net force is equal to the mass times the acceleration. So we're going to take our picture of our 5 kilogram object, and we're going to look at the forces. If I have 50 up and 50 down, they balance each other out. These are balanced forces. So they go away, which means I'm not going to draw them on this picture again because they've crossed out. Now, if I've got 15 this way and 10 this way, 10 newtons only gets rid of or only balances with 5 newtons. So what I have left is 5 newtons of force. That is the sum of my forces. I added up all of these forces, and this is what I had left over. So let's write that down. Net force, which is this sigma times F, it means sum of, or net force, is what's left over when all the forces have been added up. So net force is what's left over when all forces are added up. Well, here I have 5 newtons of net force left over. So let's do this. Sum of my forces equals mass times acceleration. 5 newtons is the sum of my forces. Mass is 5 kilograms, and we need to find the acceleration. So we divide both sides by 5 kilograms. A newton divided by a kilogram is a meter per second squared, and my acceleration comes out to be 1 meter per second squared. So that's a quick example of how we can add up the forces acting on an object. One special example that we're going to talk about with the second law is weight. Weight is the force of gravity acting on an object. We all experience weight, and we're experiencing right now. Now, weight is caused by massive objects. Primarily, that's going to mean the Earth. If we're on the moon, it's the moon, or a star, or an asteroid, or a planet, something that it's near. So for us, on planet Earth, weight is the force of the Earth pulling on a mass. Now, on the Earth, it always pulls down. Straight down towards the center of the Earth. So, if we look at an object it's going to accelerate down when we drop that object at 10 meters per second squared. We're going to start calling that g. That's the acceleration due to gravity. Okay? So, the force acting on this object, the net force acting on it, is equal to the mass times the acceleration due to gravity. Or weight, the force of gravity, is going to be equal to mass times the acceleration due to gravity. Weight is equal to mass times gravity. An important thing to look at with this is the only way to change the mass of an object, the only way to change weight you could, one, change the mass, which means you're literally taking something out of the object or putting more stuff into the object. Or you could, two, change gravity, which means you're going to another planet or you're going to the moon. That's how we change weight. Mass stays the same all the time. So your mass on the Earth is the same as your mass on the moon. But your weight on the moon is different than your weight on the Earth. Okay? Weight, the force of gravity, depends on the acceleration due to gravity. Mass just depends on how much of you is there.